Okay, in this problem, we are looking at an aluminum column that is built into the ground with a length of 2.2 meter, and it has the modulus of elasticity 70 gigapascal. And this column is experiencing axial compressive loads P. Dimensions of the cross sections are B 210 millimeters, D 280 millimeters. We are required to calculate the following. First, A, the critical load to buckle the column. B, its allowable compressive stress in the aluminum is 240 megapascal. Is the column more likely to buckle or yield? C, if the factor of safety is 1.95, what is the allowable buckling load? So let's go to step 1. First, we have to look at the equation. And this equation is the Euler buckling formula. We have seen this equation in our lecture. P critical can be calculated with pi square EI divided by LE square, L sub E square. So what is E stands for? E stands for modulus of elasticity. In this case, it's 70 gigapascal. I stands for moment of inertia. In this case, we have to look at the moment of inertia about an x-axis and y-axis to find out which one is the weak axis, which one is the stronger axis, because we know that this column is going to buckle first about its own weak axis. Let's continue with the second step. So in this step, we're going to define this LE. We already know that LE, for those of you who doesn't know what LE is, actually LE is the effective length of the column. Here the column is fixed free. It's fixed at the bottom, because if you look at the question statement, it says column built into the ground. So it's built into the ground. It cannot translate on X or Y direction, or it cannot rotate about X or Y axis. So since we know that, we have to look at the effective length from the table that we have seen in our previous lecture. I already pulled up that scenario. This is the case that we are looking at. In this case, the effective length for fixed free column LE is equal to 2L. Since we know the L is 2.2 meter, we can calculate LE by multiplying 2 by 2.2. It's 4.4 meter. Next, we have to calculate the moment of inertia. That's another unknown in this equation. As I mentioned before, we have to calculate the moment of inertia about both axes. And this stage, this column may buckle about X or Y axis, like I stated before. The moment of inertia for rectangle is BH cube over 12, and B is for base and H is for height, and we're going to use B and D in this case, and we have to calculate it for both cases. For values of B and D, you can pause this video right now and then you can do your calculation and check your numbers after. So moment of inertia about x-axis is 3.84 times 10 to the 8 millimeter to the 4th, and about y-axis 2.16 times 10 to the 8 millimeter to the 4th. In the next step, if you continue entering your number to the first equation to calculate the P critical, you can get 7,711 kilonewton for P critical. And you will see when you enter both numbers, I sub x and I sub y, moment of inertia about x-axis and moment of inertia about y-axis, you will see which number is smaller. Smaller moment of inertia governs, since it results in smaller Euler buckling loads. If in this equation, if all the numbers are the same, modulus of elasticity, effective length, and the pi is constant, then only change in variable is only change in parameter is moment of inertia. if you try both, you will see that P critical is less when you enter less moment of inertia. In the next step, we are looking at the step 2, and this is the section B. In section B, we are asked to calculate if the allowable compressive stress in the aluminum is 240 megapascal. Is the column more likely to buckle or yield? We're going to look at our good old equation P over A for stress calculation. The critical buckling stress is the Euler buckling load divided by the area. So Euler buckling load is already calculated 7711 kilonewton. And if you calculate the area, B times D, you can pause this video and you can calculate and you can check your number with me. Let's continue. I already calculate the critical stress for buckling. It's 131.1 megapascal. In the next step, we're going to look at the two scenario, and this two scenario is going to tell you which one is going to occur first: yield stress or failure because of the yielding of the material, or failure because of the buckling of material. So in the first scenario, if the critical stress is less than 240 megapascal, the column will buckle. Since as the load is applied, the buckling stress is reached first. So let's look at it this way. So if I have 131.1 megapascal, if I reach already 131.1 megapascal during the experiment, let's say we are loading this column, is it going to buckle? Yes. Before it reached 240 megapascal, before it yields. But on the other scenario, if I start applying load, and in this case the critical buckling stress is bigger than 240 megapascal, the column will yield. Since the yield stress Sy, 240 megapascal is reached first. It's very simple. And let's look at the next step. In the step 3, we are answering the section C. If the factor of safety is 1.95, what is the allowable buckling load? With respect to buckling only, the allowable load on the column, P allowable, for a factor of safety 1.95. The factor of safety is defined as failure loads divided by the allowable load. In this case, we know the failure load, which it was 7711 kilonewton. If we divide that number by 1.95, we will get 3954 kilonewton. This will give us the answer for this problem.